In the YouTube video titled Lecture 16, Introduction to Elliptic Curves by Christof Paar, Professor Paar, a leading figure in the field of cryptography, commences his lecture by extending a cordial welcome to his students upon their return from the Easter holiday. This informal greeting sets a friendly tone for the ensuing exploration of a foundational concept in modern cryptography: elliptic curves. Par's discourse delves into the mathematical intricacies of elliptic curves, highlighting their unique properties and their divergence from traditional curves. He underscores the paramount importance of grasping the group structure inherent to elliptic curves, emphasizing the additive operation and its profound connection to the group's underlying properties. Paar elucidates how this operation facilitates efficient computations and lays the groundwork for the development of secure cryptographic algorithms. Professor Paar leverages visual aids and concrete examples to facilitate student comprehension of these complex mathematical concepts. He demonstrates the applicability of elliptic curves in the realm of cryptography, specifically in the context of elliptic curve cryptography, ECC. He articulates the significant advantages offered by ECC over traditional cryptographic algorithms, particularly in terms of efficiency and security. The lecture culminates with a concise overview of the diverse applications of elliptic curves in contemporary cryptography, encompassing their utilization in digital signatures, key exchange protocols, and secure communication systems. From 0 minutes to 5 minutes of the video, Professor Paar warmly greets the students, inquiring about their well-being after the Easter holiday. His opening remarks establish a casual and welcoming tone, setting the stage for the academic discourse to follow. He then seamlessly transitions into the core topic of the lecture: Introduction to Elliptic Curves. While the provided transcript does not reveal the specific details of his introduction, it is highly likely that Professor Paar introduces the foundational concepts of elliptic curves, emphasizing their significance in modern cryptography. He might delve into the mathematical definition of an elliptic curve as a set of points x, y, satisfying a specific equation, or he may explore the geometric properties of these curves, laying the groundwork for subsequent discussions on their cryptographic applications. From 5 minutes to 5 minutes of the video, the speaker begins by greeting the audience and making a lighthearted remark about the Easter break. They do not discuss elliptic curves or any related mathematical concepts in this short excerpt. From 10 minutes to 15 minutes of the video, Professor Paar initiates a discussion on the significance of elliptic curves in the realm of cryptography. He commences by elaborating on the mathematical definition of elliptic curves, which are characterized by equations of the form y superscript 2 equals x superscript 3 plus x plus b, where a and b represent constants. This equation geometrically manifests as a specific curve in the xy plane, which is precisely what is termed an elliptic curve. Professor Paar then introduces the notion of points residing on the elliptic curve, which are represented by coordinate pairs x, y, that satisfy the defining equation. Notably, he emphasizes that the addition of points on an elliptic curve is not performed through conventional arithmetic operations. Instead, it is achieved through a geometric procedure that involves drawing a line connecting 2 points on the curve and determining the third point at which the line intersects the curve. The coordinates of this third point, after being reflected across the x-axis, constitute the sum of the 2 original points. From 15 minutes to 20 minutes of the video, Professor Paar introduces the concept of elliptic curves, explaining that they are algebraic curves defined by an equation of the form y superscript 2 equals x superscript 3 plus x plus b. He then focuses on the specific case of the curve y superscript 2 equals x superscript 3x, emphasizing its symmetry and the existence of a point at infinity, denoted as O. The professor clarifies that elliptic curves are not ellipses in the geometric sense. He proceeds to illustrate the addition operation for points on the curve by drawing a secant line connecting 2 points, determining its intersection with the curve, and reflecting that point across the x-axis. Professor Paar goes on to highlight the associativity property of point addition, meaning that p plus q plus r equals p plus q plus r. He demonstrates this property by adding the points 1, 0, and 2, square root 2, on the curve y superscript 2 equals x superscript 3, x, showing that their sum is -1, 0. From 20 minutes to 25 minutes of the video, Christof Paar commences his discourse on the fundamental concept of elliptic curves, emphasizing their profound implications for the realm of cryptography. He underscores the crucial distinction between elliptic curves and their namesake, ellipses, clarifying that elliptic curves are not geometrically related to ellipses. Instead, they are defined by a specific algebraic equation of the form y superscript 2 equals x superscript 3 plus x plus b, where the constants a and b govern the curve's shape and position. Illustrating this abstract concept, Paar presents a concrete example by setting a equals 2 and b equals 1, yielding the equation y superscript 2 equals x superscript 3 plus 2x plus 1. This equation, he explains, represents a curve embedded within the xy plane, with a notable point located at coordinates x equals 0 and y equals 1. Furthermore, Paar introduces the notion of addition within the context of elliptic curves, where given 2 points, P and Q, a novel point, R, is derived by drawing a line through P and Q, identifying their third intersection point with the curve, and reflecting it across the x-axis. This unique operation forms the bedrock of elliptic curves application in secure cryptographic protocols. From 25 minutes to 30 minutes of the video, Professor Paar initiates a discourse on the fundamental role of elliptic curves in modern cryptography. He commences by elucidating the defining equation of an elliptic curve, which takes the form y squared equals x cubed plus x plus b, where a and b are constants. This equation represents a curve embedded within a two-dimensional plane. Professor Paar then elaborates on a specific instance of an elliptic curve defined by the equation y squared is equal to x cubed plus 2x plus 2, showcasing how to determine points lying on this curve. He exemplifies this by substituting x equals 1, yielding y squared equals 1 plus 2 is equal to 5, and subsequently solving for y, obtaining y equals plus or minus square root 5. Consequently, the points 1, square root 5, and 1, dash square root 5 are identified as belonging to the elliptic curve in question. From 30 minutes to 35 minutes of the video, Professor Paar delves into an illustrative example of elliptic curve cryptography, highlighting its application in safeguarding digital communications. He commences by introducing the fundamental concepts of a public key and a private key associated with a user named Alice. He then proceeds to demonstrate how Alice can leverage her private key to generate a digital signature for a message, effectively authenticating her identity. This signature, intricately intertwined with the message itself, is subsequently transmitted to Bob, who can then utilize Alice's public key to verify the signature's legitimacy and thereby confirm the message's authenticity. The procedure involves a multiplication of the private key with a point on the elliptic curve, resulting in a new point on the curve that serves as the digital signature. The public key, a derivative of the private key, is generated through a process involving a generator point and scalar multiplication. Multiplying the generator point by the private key yields the public key. This elegant construction ensures that the public key cannot be exploited to infer the private key, guaranteeing the system's robust security. From 35 minutes to 40 minutes of the video, Professor Paar embarks on a detailed exposition of the intriguing operation of adding points on an elliptic curve. He emphasizes that this addition is not the familiar arithmetic addition, but rather a geometric operation uniquely defined by the inherent properties of the elliptic curve. This process, which he elaborates upon with illustrative examples, involves the following steps. 1. Line construction *. A line is drawn connecting 2 points that lie on the elliptic curve. 2. Third intersection *. The point where this line intersects the curve for the third time is identified. 3. Reflection *. This third intersection point is then reflected across the x-axis. The resulting point is deemed the sum of the original 2 points. Professor Paar clarifies this concept with a concrete example involving the points 2, 3, and 4, 5, situated on a specific elliptic curve. He demonstrates that the line connecting these points intersects the curve at a third point, -2, 1. Reflecting this point across the x-axis yields -2, -1, which he identifies as the sum of the original 2 points. Professor Paar underscores the pivotal role of this geometric addition in the field of cryptography, highlighting its foundational importance in elliptic curve cryptography, ECC, a highly secure cryptographic system. From 40 minutes to 45 minutes of the video, Professor Paar transitions from the theoretical groundwork of elliptic curves to their practical applications in cryptography. He focuses on the specific elliptic curve equation y squared equals x cubed plus x plus b, highlighting its suitability for cryptographic purposes. This equation's key feature is its inherent group structure, established through the addition of points on the curve. This group structure forms the foundation for cryptographic operations, enabling efficient and secure computations. Professor Paar then introduces the concept of scalar multiplication within the context of elliptic curves. This involves repeatedly adding a point on the curve to itself a predetermined number of times. For example, multiplying a point p by a scalar 3 equates to adding p to itself thrice, resulting in 3p. The efficiency of scalar multiplication lies in its capacity to execute complex operations using relatively simple additions. Finally, Professor Paar stresses the critical importance of meticulously selecting parameters for cryptographic applications employing elliptic curves. He emphasizes the need to prioritize the security of the chosen curve, particularly by selecting a large prime number p for the finite field where the curve is defined. This prime number serves as a crucial element in preventing potential attacks and safeguarding the integrity of cryptographic operations. From 45 minutes to 50 minutes of the video, Professor Paar delves into the fundamental operation of point addition on an elliptic curve. He elucidates the process of adding 2 points, denoted as P and Q, by constructing a secant line connecting these points and identifying the third intersection point of this line with the curve. This third point is then subjected to a reflection across the x-axis, yielding the resultant point, designated as P plus Q. In the special case where P and Q coincide, a tangent line to the curve at the point is employed instead of a secant line, with the same reflection procedure applied to obtain the sum. Professor Paar then provides a concrete illustration by adding the points 1, 2, and 2, 3 on the elliptic curve defined by the equation y squared is equal to x cubed plus x plus 1. Drawing a secant line through these points, it is observed to intersect the curve at 0, 1. Reflecting this intersection point across the x-axis results in the sum 0, 1, representing the point P plus Q. From 50 minutes to 55 minutes of the video, Professor Paar delves deeper into the mathematical foundations of elliptic curve cryptography. He elucidates the concept of group operation on an elliptic curve, emphasizing that it involves a non-standard addition of points on the curve. This operation is defined geometrically rather than algebraically. Professor Paar provides a concrete illustration by demonstrating the addition of 2 points, P and Q, to yield a third point, R, on the curve. The process involves drawing a secant line through P and Q, identifying the intersection of this line with the curve, and finally reflecting this point across the x-axis to obtain R. This geometric addition is crucial for the security of cryptographic systems based on elliptic curves, as it possesses the essential property of associativity. P plus Q plus R equals P plus Q plus R. Professor Paar underscores the significance of this property for the robust security of elliptic curve cryptography. From 55 minutes to 60 minutes of the video, Professor Paar delves into the intricate algebraic structure of elliptic curves, introducing the fundamental concept of the group law that governs operations on points lying on the curve. He elucidates that the addition of 2 points on the elliptic curve entails drawing a secant line passing through them, identifying the third intersection point, and subsequently reflecting this point across the x-axis. This geometric operation yields the sum of the 2 initial points. To visually illustrate this principle, he demonstrates the addition of 2 points, A and B, resulting in point C. Professor Paar then introduces the notion of scalar multiplication, whereby a point on the curve is multiplied by an integer. For instance, multiplying point A by 3 entails repeated addition of point A to itself 3 times, culminating in point D. Finally, he emphasizes the paramount importance of the group law in cryptographic applications, highlighting its capability to define a cyclic group with a generator point and its associated order, which corresponds to the total number of points on the curve. From 60 minutes to 65 minutes of the video, Professor Paar commences his exploration of elliptic curves by introducing the concept of point addition. He initiates the discussion by defining an elliptic curve over a finite field, which is mathematically represented by the equation y squared equals x cubed plus x plus b, where a and b are constants. To determine the sum of 2 points, P and Q on this curve, one constructs a line connecting them and identifies the third point of intersection, denoted as R. The additive inverse of point R, represented as R, is then defined as the sum of P and Q. Professor Paar substantiates this concept with a concrete example utilizing the elliptic curve y squared is equal to x cubed plus 2x plus 1, and the points P equals 2, 3, and Q equals 1, 2. The line connecting P and Q intersects the curve at point R equals -1, -2, leading to the conclusion that P plus Q equals R equals 1, -2. Professor Paar concludes this segment by emphasizing that point addition on elliptic curves is inherently defined over a finite field, rendering it a discrete operation. From 65 minutes to 70 minutes of the video, Professor Paar introduces the concept of elliptic curves defined over finite fields, specifically focusing on the field of integers modulo a prime number, denoted as Fp. He emphasizes that these curves are not ellipses in the traditional geometric sense, but are defined by an equation of the form y squared equals x cubed plus x plus b, where a and b are elements of Fp. The professor then delves into the fascinating properties of these curves, highlighting that they possess a group structure, meaning they are closed under a specific addition operation. This implies that given 2 points on the curve, their sum, as defined by this operation, will also be a point on the same curve. To illustrate this crucial concept, he uses a specific example, where the curve is defined by y squared is equal to x cubed plus 2x plus 2 in the field F5, representing the integers modulo 5. He then demonstrates the addition operation by taking 2 points, P equals 0, 2, and Q equals 2, 1, and calculating their sum R equals P plus Q. To find R, a line is drawn through P and Q, and the point where this line intersects the curve is reflected across the x-axis to obtain R. The professor explicitly shows that R equals 1, 3 is indeed a point on the curve, thus validating the group structure of elliptic curves over finite fields. From 70 minutes to 75 minutes of the video, Professor Paar delves into the potent application of elliptic curves within the realm of cryptography. He commences by elucidating the concept of a group, emphasizing the fundamental nature of the group operation. He then defines an elliptic curve as a geometric locus of points satisfying a specific algebraic equation. Professor Paar visually demonstrates the group operation on an elliptic curve, which involves constructing a secant line through 2 distinct points and identifying the third intersection point. He explains how this procedure generates a group structure on the curve, paving the way for the application of abstract algebraic principles to cryptography. The concept of a generator point is introduced, revealing how repeated application of the group operation on a single point can generate all other points on the curve. Professor Paar concludes by introducing the concept of a finite field, where the coordinates of points on the elliptic curve are constrained to a specific finite set of values. This restriction, he explains, makes it possible to implement elliptic curve cryptography in practical cryptographic applications. From 75 minutes to 80 minutes of the video, Professor Paar delves into the fundamental algebraic structure of elliptic curves. He introduces the concept of a group operation on elliptic curves, demonstrating how 2 points, P and Q, can be added using geometric constructions. He outlines the process of drawing a line connecting P and Q, identifying the intersection of this line with the elliptic curve, and then reflecting this intersection point across the x-axis to obtain the sum P plus Q. Professor Paar emphasizes that this group operation adheres to the axioms of a group, signifying that it is associative, has an identity element, and each element possesses an inverse. This group structure is paramount in the application of elliptic curves to cryptography, as it forms the foundation for constructing secure cryptographic systems. He clarifies that while the group operation on elliptic curves is presented geometrically, it can be expressed algebraically as well. He further elucidates the concept of finding the inverse of a point P by reflecting it across the x-axis. He then introduces the operation of scalar multiplication, which involves repeated addition of a point P to itself a specified number of times, exemplified by 3P equals P plus P plus P. Professor Paar highlights the significance of efficient algorithms for performing scalar multiplication, given the potentially large number of additions required. From 80 minutes to 80 minutes of the video, The speaker welcomes viewers back after the Easter break. The video then dives into the realm of elliptic curves within the context of cryptography. A foundational concept is introduced: elliptic curves over finite fields. The speaker meticulously demonstrates how to calculate points on an elliptic curve using the equation y squared equals x cubed plus x plus b, where the constants a and b are defined within a specific finite field. The speaker highlights that this equation defines an elliptic curve, with points on the curve represented as ordered pairs, x, y. An essential point is made. The number of points on an elliptic curve is finite and can be determined using the Hasse theorem. This theorem posits that the number of points on an elliptic curve over a finite field is approximately equal to the size of the field, with a slight deviation.